This is my model of a hydroelectric dam, and I'm actually going to link this to a recent FIQ question which actually asked how we can generate electricity from a hydroelectric dam. So you can see the diagram is here on your question, and it asked where does the kinetic energy of the water become transformed into mechanical energy, and of course it's at that point where there's a turbine. And then it says, explain why the water in the storage reservoir has potential energy that is useful in hydroelectric power generation. So you can see in my model here, this is just what I found in my laboratory, that you can see that the ice cream container full of liquid is meant to represent the dam. And if you've ever walked and had a look at a dam, you'll notice that there's usually the power station or the little hydro stations right down at the bottom, and the water is higher up, and it's really quite strong and big, and often you can't see this, but the opening where the water comes out is quite small. I've used a straw to represent that. Now the whole concept with this process of generating electricity is that we want to be able to have this water at a high level, because the gravitational force gives that water potential energy, and that water gushes out through a whole heap of pressure far more forcefully if it's through a small opening rather than a big opening, and it moves what we call the turbine around. Okay, so this is our turbine, and the piece of copper wire or any wire, whatever they use, is attached to this turbine, and the turbine rotates around and around with the wire on top of it. Now this all takes place next to a giant magnet, and what we notice is when we have that combination of a moving coil of wire next to a magnet, we get electricity being produced. Okay, so you can see that I've tried to represent this. I can't move it and actually demonstrate this to you at the same time because I'm holding my phone, but you can see that this is meant to basically show the charge that's created. And then what happens is we take that charge, we reduce the amount of charge, and we send it out to substations, and then we use that electricity to our homes, which is at a much safer voltage. Okay, so that's our overall model of how we use hydroelectric dams to generate electricity, and I've linked that to one of your most recent FIQ questions. This is our model for understanding geothermal energy, and you can see I've tried to replicate that this hot plate's meant to represent that we have a whole pocket of hot water deep underneath the Earth's crust, and it's channeled out, and you can see I've used that as a straw, and that when we have that steam that comes out, we use it to generate and move our coil of wire around, which is next to a magnet, and we get the generation of electricity being produced, and then we can use that electricity to heat our homes, or even in the cases for geothermal energy, a lot of it is used to heat swimming pools. Sometimes in some countries even their sidewalks are even heated. Now, some important bits of information to remember about this topic is that geothermal stations can either be dry steam, which is where we basically directly use the steam to power the power stations, or it can be flash steam. And flash steam is really more concerned with using that steam and placing it under tanks under controlled conditions, and basically utilizing the differences in pressure and temperature to drive the turbines. Okay, now geothermal energy, remember, is used in countries such as Iceland and New Zealand. There are some regions in the States that also use it, such as Yellowstone National Park. Some of the cons of this type of energy is that there are some volatile elements under the ground, such as mercury and arsenic, and some noxious gases. Hydrogen sulfide is a noxious gas that's been produced, and recent technology has looked at ways of trying to eliminate that type of contamination. So scrubbers and abatement technologies actually have been developed to try and remove those noxious substances while maximizing heat energy output. Okay, so this is our natural gas model, and usually natural gas, I guess in the States, it's a non-renewable resource, and there's actually quite a good amount of reserves in the US. But I'm just going to show you a model of how natural gas extraction actually takes place. So first of all, someone has to locate a resource or an area where there are natural gas deposits, and they would have to mine or be able to change the terrain to be able to access it. So you can see that I'm replicating this using scissors. And then they would have to create a method to be able to extract the natural gas. So we've been learning about this in class, that fracking is actually used. And to represent the fracking process, I'm using this can. And in real life, they would stick pressurized liquid into an area where they would discover the natural gas reserves. And if you look closely in here, this is, I've just opened it up so you can see, but obviously they would find a small area and they would push this pressurized liquid in, and what happens is they would push it in and they would release the gas. Okay, so you can see that I've done that, and what I'm going to do is I'm going to try and capture some of these gases, and you can see it's actually flammable, which gives you an indication as to what that particular type of gas is. Now obviously there's a lot of issues with this type of I guess process of getting the gas, because what we have happening is we have a lot of, let me just use a blue pen, groundwater contamination, especially on top and underneath from completing the process of being pushing those high pressurized liquids in, and also we just generally have a lot of habitat disturbance as well. Okay, so this is our next type of energy source, and this is a focus on batteries. Okay, so we all know what batteries are. Batteries are basically used to power portable devices such as cell phones or laptops, and they can also be used to supply electricity to cars and trucks. There's loads and loads of different types of batteries, but basically they all work by converting chemical energy into electrical energy. So one of the great things about batteries is that they don't release combustion byproducts that contribute to climate change. However, there are some cons to using batteries, because they can potentially leak electrolytes, which are toxic, so substances such as lead, cadmium and mercury, and often too batteries can actually explode when they're overcharged or misused. So at the moment, as part of I guess an environmental initiative, lots of workplaces are organising areas where you can actually dispose of batteries safely. So this little particular exercise is just comparing the differences between a 9-volt battery and a D battery, and you can see that I'm just using basically a multimeter to be able to take a reading between the two. So I've put copper on the end, and I should be able to see, if you look closely, that the needle is moving, okay, indicating that I've got a charge. The needle just moves right to the end. It's really difficult to actually compare the differences between these two batteries on this particular machine, but nevertheless we'll give it a go anyway. But on your lab sheet you can think a little bit about the differences of the volts on the batteries, and here's a lovely little diagram that I found of voltage. It's a force basically that pushes the current along. So the applications for these two batteries, this one is used for, so it's got a 1.5 volt. It's used for like high intensity kind of equipment. So for example, a flashlight, whereas this 9 volt it can be used for a really, really long period of time. So an example I can think of here at school is it would be plugged into, say, the temperature sensor of when we walk into school in the morning. So just example of what batteries are, and a little bit of information about how batteries work. Okay, so this is our next energy source, which is coal. I'm just going to put some of the paper so you can see it. Okay, looks like it's high grade anthracite coal. So I'm going to put this into my test tube, and you can see that on this test tube there's a small hole on the bottom down here. Okay, so obviously we can like observe or test the gas that's produced from this reaction. I'm going to put this cork on top, and then I'm going to gently heat the coal, and we're going to burn it. Now simultaneously I've got a lit toothpick here. So we want to test the gas. We should be producing either carbon monoxide or carbon dioxide, and we know that through our gas test that it should extinguish a splint. Let's see if we get the gas being produced. Not really clear to see that it's going to extinguish it, but actually that would be the gas produced. Something else to just point out to you here is that it's not a clean burn, and there's a lot of black carbon monoxide left behind, or residue left behind in the test tube that you can see there. There's a bit of gas. Yes, and it does, and it extinguishes that flame. Again, this is a very basic model of an example of wind as a resource for energy. You can see I have made a model of a wind generator. So again, the same concept. The power of the movement of the wind moves the wind generator, which moves the turbine next to the magnet, which then sends that charge to a substation, and that is delivered out into our homes. This is a simple example of how we can create two different gases from using an electric current to be able to split the components of water. Okay. So Michael Faraday was actually the man that discovered this process a long time ago, and he called it electrolysis. So what it is basically two metal rods in water, and you can see there's inverted test tubes there. There's a negative and a positive end, and these two metal rods are called electrodes. Okay, so they're basically connected to a power supply. So in class we sort of talked about that hydrogen could possibly be used as a substitute for fossil fuels, and it's currently being investigated. And it would be amazing if we could use this resource, because we basically have an unlimited supply of hydrogen in water. But the problem with it is that to be able to create this process, we need electricity to be able to kickstart the reaction. So that's one of the major problems, is that we need to kind of think of new ideas about how we can actually use that electricity to start this reaction off. And at the moment, just reading about new research and ideas, they're starting to look at using solar panels to be able to generate this particular reaction. Okay, so you can see here that in one test tube there's going to be hydrogen gas being produced, and basically electrons are going to be gained and the hydrogen gas is going to be reduced. And on the other test tube, oxygen gas is going to be created. In fact, sometimes if you look really closely, you can see air bubbles popping. It looks orange. There's a salt inside the solution, which is sodium sulfate, and we use that because when we generate the current, we have to be able to basically be able to move those charged ions. So what I'm also going to do to work out hopefully which gas is in which area is the area where there's been the cathode should turn blue to indicate that there's OH minus ions, and the other area should be yellow to indicate that there's H plus ions. So let's just see if that's actually going to work. Possibly it might not. Should get different colours depending. It's been actually going for quite a while, so maybe not. Maybe I'll come back and double check on that. I think the this particular side looks slightly more blue than the other, so maybe that's where the OH minus ions have actually gone, and maybe we'll get hydrogen in this test tube. Let's just see. 3, 2. Okay, so what I'm going to do is I'm going to do some gas tests to try and figure out. I've used a bromothiol blue, but it's not really that clear as to which end is producing hydrogen and which is producing oxygen. And what I'm going to do is lift it, put the bubbles of gas out, and see what happens with the flame. So to me that looks like it's been extinguished, or maybe lit. Let's just do the other one. Maybe we'll get a popping sound. I should get one test tube that makes a pop indicating that hydrogen's been produced, and one test tube that should relight a glowing splint. Tip the water out. Okay, that was definitely oxygen because it really relit the glowing splint. So I do believe I was correct that this one here was hydrogen. It just didn't make a loud enough pop, and this one was oxygen. Thanks, that's it.